projects. In this video, we are going to explain about the project title, A Gradient Boosting Approach for Training Convolutional and Deep Neural Networks. Introduction. Deep learning methods, particularly convolutional neural network CNN and deep neural network DNN, have immense attention in the field of computer vision and image classification. These networks excel in recognizing patterns and features within images, making them pivotal for tasks like object recognition, image classification, segmentation, and more. CNNs have become the go-to architecture for numerous computer vision tasks due to their ability to extract hierarchical representations from images. Their applications extend across various tasks such as image classification, assigning a label to an entire image, object detection, identifying and locating multiple objects within an image, anomaly detection, spotting irregularities or outliers, and segmentation, dividing an image into meaningful segments. As neural networks get deeper, training becomes more challenging. One notable issue is vanishing gradients, where gradients become extremely small as they propagate backward through many layers, leading to slow training. Solutions like batch normalization, normalizing inputs within each mini batch during training, and architectures like residual neural network (ResNets) that use skip connections to ease gradient flow have been introduced to elevate these challenges. GBM gradient boosting machines like XGBoost and LightGBM have become highly effective for tabular data tasks involving classification and regression. These methods work by combining multiple weak learners, typically decision trees, to create a strong predictive model. Interestingly, there have been efforts to incorporate GBM gradient boosting machines into training neural networks, leveraging their strengths in optimizing complex models. In this project, we have introduced two innovative training architectures, GBCNN, that is Gradient Boosting Convolutional Neural Network, and GBDNN, Gradient Boosting Deep Neural Network. These architectures utilize the gradient boosting procedure to construct a series of embedded neural networks in depth. GBCNN is designed for training convolutional neural networks using a boosting approach, potentially enhancing performance in computer vision tasks. On the other hand, GBDNN offers a simpler architecture tailored for tabular data, aiming to leverage the benefits of gradient boosting in this domain. Objective. The primary goal of this project is to introduce two innovative training architectures, GBCNN and GBDNN. These architectures are tailored for training convolutional neural network CNN and deep neural network DNN, respectively. Both architectures leverage gradient boosting, a technique known for its effectiveness in combining weak learners to create a strong predictive model. The key aim of implementing GBCNN and GBDNN is to enhance the performance metrics, particularly in terms of classification accuracy of CNNs and DNNs. By utilizing the boosting methodology, these architectures target improved accuracy over traditional CNN and DNN models. The proposed models undergo an iterative training process. They are trained sequentially, where each subsequent model aims to fit the gradient of the loss function or pseudo residuals left unexplained by previous models. This iterative approach gradually refines the model's predictions by focusing on areas where the previous models underperformed. To mitigate overfitting and allow for more effective learning in subsequent iterations, the weights of the dense layers trained in previous iterations are frozen. This strategy prevents the model from excessively fitting to the training data and enables it to focus on learning new information in the subsequent layers while fine-tuning the convolutional layers. The ultimate objective is to capture and learn information that previous iterations have missed. By iteratively fitting the residual information and freezing the weights of certain layers, these architectures aim to achieve superior performance compared to standard CNN and DNN models with identical architectures. This pursuit of unexplored information helps enhance the model's predictive capabilities and potentially yields better result in classification tasks. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following steps. The first step is importing the packages. This step involves importing the necessary libraries and packages required to work with data, perform computations, and implement machine learning models. Common packages include TensorFlow or Keras for building neural networks, NumPy for numerical operations, Matplotlib for visualization, and other relevant libraries. Exploring the dataset. The project involves working with several datasets. MNIST, a dataset of handwritten digits 0 to 9 used for image classification task. CIFAR 10, a dataset containing 10 classes of various objects, example airplanes, cars, birds, etc., suitable for image classification. Rice varieties, a dataset related to different types or varieties of rice grains for classification or analysis. Fashion MNIST, similar to MNIST but with fashion related items like clothes and accessories for classification. Rock, paper, scissors, a dataset depicting images of hands showing rock, paper, or scissors, often used for gesture recognition. Exploring these data sets involves loading, visualizing, and understanding the structures of the data, such as the number of samples, labels, and image sizes. This step allows to prepare and pre-process the data for model training. Image processing. Using the image data generator from libraries like Keras, rescaling the image. Normalizing pixel values to a specific range, example 0 to 1 for faster and more stable training. Shear transformation, distorting images by shifting one part of the image in a fixed direction. Zooming the image, altering the scale of the image either by zooming in or out. Horizontal flip, flipping images horizontally to augment the dataset and provide variations for the model to learn from. Reshaping the image, adjusting the dimensions or shape of images to fit the network's input requirements. Example, resizing images to a specific size. Feature extraction using Hog model. Reading the image, loading images from the dataset or user input. Resizing the image, adjusting the size of images to a predefined dimension for consistency in feature extraction. Convert the color. Converting the color space of images if required, for example, from RGB to grayscale. Appending the image and labels. Combining processed images with the corresponding labels or classifications. Conversion to NumPy value. Transforming image data into NumPy arrays for compatibility with machine learning models. Label encoding. Assigning numerical labels to categorical classes for model training. Building the model. Designing the architecture of the model, which includes the novel architectures GBCNN and GBDNN based on gradient boosting, as proposed in the project. This involves defining layers, activation functions, optimization algorithms, loss functions, and any specific configurations relevant to the proposed architecture. Training the model. Utilizing the prepared and proposed dataset to train the model. This involves feeding the data into the model, iteratively adjusting the model's parameters to minimize the loss function, and optimizing its ability to make accurate predictions. Flask framework with SQLite for sign up and sign in. Implementing a web application using the Flask framework, incorporating functionalities for user registration sign up and authentication sign in using a SQLite database. This allows users to create accounts and log in securely to access the application's feature. User upload an image for analysis, providing a feature where users can upload images for analysis through the web interface. This uploaded image will be used for prediction by the trained model. The given input is pre-processed. Before using the image for prediction, pre-processing steps similar to those performed during feature extraction are applied to the user uploaded image. This ensures that the input image is compatible with the model's requirements. The trained model is used for predicting the result. Utilizing the trained model to make predictions on the pre-processed user uploaded image. The model will provide a classification or output based on the learned features from the training data. Final outcome is displayed, presenting the predicted result or outcome based on the uploaded images analysis. This could be the classification label or probability distribution over classes or any other relevant information that demonstrates the model's prediction to the user. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is CNN, Convolutional Neural Network, a deep learning architecture specifically designed for processing structured grid-like data like images. CNNs consist of convolutional layers that extract features from input images, followed by pooling layers to reduce dimensionality and fully connected layers for classification. CNN are a fundamental part of computer vision task in the project. They serve as the base architecture for image classification and feature extraction. GBCNN, Gradient Boosting Convolutional Neural Network. This architecture combines the concept of gradient boosting with CNN. It employs a boosting technique to train multiple iterations of CNN sequentially, aiming to improve performance by focusing on residual errors left unexplained by previous models. GBCNN are a novel extension proposed in the project using boosting to enhance the capabilities of CNN for image classification tasks. DNN, Deep Neural Network, a type of neural network consisting of multiple hidden layers between the input and output layers. DNNs, Deep Neural Network, are known for their ability to learn intricate patterns and representations in data. DNN is used for tasks beyond image processing, possibly handling tabular data or other types of structured data. GBDNN, Gradient Boosting Deep Neural Network. Similar to GBCNN, GBDNN applies the principles of boosting to DNNs. It involves training multiple iterations of deep neural networks in a boosting framework, aiming to enhance performance by iteratively focusing on residual errors. GBDNN are likely an innovation introduced to leverage boosting techniques in enhancing the performance of deep neural networks for specific tasks. XGBoost, Extreme Gradient Boosting. XGBoost is an ensemble learning method on decision trees. It's renowned for its speed and performance in handling tabular data and can be applied to both regression and classification problems. XGBoost is utilized as a standalone model or as a part of an ensemble method to complement the predictions generated by neural networks. As an extension, we applied an ensemble method that combines the predictions of multiple individual models to produce a more robust and accurate final prediction. Flask, a micro-web framework, is used to create a user interface where users can interact with the trained models. Authentication mechanism secures user access. Flask is utilized to build a web-based interface allowing users to upload images, trigger predictions using the trained models, and display the results securely. Comparison graphs. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. These are the comparison graph of CIFAR dataset. This is the accuracy comparison graph. Here on the x-axis we have accuracy score and on the y-axis we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is the precision comparison graph. On the x-axis we have precision score and on the y-axis we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is the recall comparison graph. On the x-axis we have recall score and on the y-axis we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. Here on the x-axis we have FN score and on the y-axis we have algorithm name. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. We will consider the model which is performing well compared to other models. Comparison graphs of fashion dataset. In this project, we have also utilized fashion dataset. So models are compared with the parameters accuracy, precision, recall, and FN score. Comparison graph of MNIST dataset. Models are compared with the parameters accuracy, precision, recall, and FN score. Comparison graph of RISE dataset. This is the accuracy comparison graph. This is the precision comparison graph. This is the recall comparison graph. And this is the FN comparison graph. In this project, we have also utilized RPS dataset. And these are the comparison graph of RPS dataset. Models are compared with the parameters accuracy, precision, recall, and FN score. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes pages like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. These are model files which contain algorithm information which will be loaded into the project code during runtime. This is notebook folder. This notebook folder contains Jupyter Notebook files, which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, this localhost, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register, but I have already registered myself. So click on sign in. So here we need to enter the username and the password which we have created, and then click on login button. We have logged in successfully. So here we can see we are having the prediction link. Click on it. So here we can see we are having three different data sets. So we will execute the project using these data sets. First, click on CIFAR 10 data set to execute the project. So here we need to upload the image to classify the image. Now click on choose file to upload the image. Select the image and then click on open. Now click on upload button. So here we can see this is the uploaded image and this image is classified as deer. Now we will upload some more images and check the classification of the images. Click on choose file. I'm selecting this image. Now click on open. Now click on upload button. So here this is the uploaded image and this image is classified as cat. We will upload some more images. Click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and this image is classified as automobile. Click on try again. Click on choose file. I'm selecting this image, click on open. Now click on upload button. This is the uploaded image and this image is classified as dog. In this way, by uploading the images, we can do the classification of the images. Now we will do the prediction using another data set, which is rice varieties. Click on it. Now click on choose file to upload the image. Now again, click on choose file. Select the image and then click on open. Now click on upload button. So here, this is the uploaded image and this image is classified as Jasmine. Now we will upload some more images. Click on choose file. Select the image, click on open. Now click on upload button. So here, this image is classified as Ipsala. Now click on try again. Click on choose file. Select the image, click on open. Now click on upload button. This image is classified as Basmati. Now click on try again. Click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and this image is classified as arborio. In this way, by uploading the image, we can classify the varieties of the rice, whether it is arborio, basmati. Now we will do the prediction using another algorithm, which is RPS. So click on it. Now click on choose file. Select the image, click on open. Now click on upload button. This is the uploaded image and this image is classified as rock. Now click on try again. We will upload some more images. Click on choose file, select the image, click on open. Now click on upload button. This is the uploaded image and this image is classified as paper. Now click on try again. We will upload one more image. Click on choose file, select the image, click on open. Now click on upload button. This is the uploaded image and this image is classified as Caesar. In this way, by uploading the image, we can classify them as rock, paper, Caesar. So we have done the prediction using three different data sets, CIFAR10, rice varieties and RPS, which is rock, paper, Caesar. Now click on sign out button. The conclusion of the project is the models GBCNN and GBDNN employing gradient boosting exhibit better performance in classification accuracy when compared to standard CNN and DNN models. This improvement suggests that the boosting methodology enhances the model's ability to learn and make more accurate predictions. Across diverse 2D image classification and Tableau datasets, the proposed GBCNN and GBDNN consistently outperform baseline models. This consistency in superior performance across different datasets implies the robustness and generalizability of the proposed models. The iterative training approach of adding one dense layer to an exact copy of the previous model offers a controlled way to fine tune the models. This incremental addition helps in refining the model's predictions by adjusting the dense layers while preventing overfitting. The strategy of freezing weights in the dense layers trained in previous iterations allows the models to leverage information already learned while focusing on capturing new and unexplored information in subsequent iterations. This helps in avoiding redundancy in learned features and improving the model's understanding of complex patterns in the data. The promising results obtained from GBCNN and GBDNN signify the potential of utilizing gradient boosting techniques to train CNNs and DNNs effectively. Leveraging gradient boosting appears to be a fruitful strategy for enhancing the learning and predictive capabilities of these neural network architectures.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.